All right, we're going to finish up our kinetics unit by talking about catalysis. So catalysis, a catalyst, is something that increases the rate of a chemical reaction. You probably are familiar with the term, you've probably heard it a lot, and kind of the classic definition is a catalyst is something that speeds up a reaction without being used itself. What it means in terms of kinetics is it speeds up the reaction or increases the rate of the reaction by providing a mechanism with a lower activation energy. So in other words, we've looked at mechanisms that kind of cause a reaction to happen overall. So those different elementary steps that happen. What a catalyst will do is somewhere in one of those elementary steps, it'll actually add in an elementary step with a lower activation energy. So let's say normally a reaction, it looks like this to happen. A catalyst will put a step in there so that now the activation energy is lowered. So you still get the same final products, but the activation energy is lower, therefore it can happen quicker. It doesn't take as much energy, or it can use more of its energy to get over that hump and produce more products. The classic definition, they are not produced or consumed in the reaction, so that means they're there before the reaction starts, and they're there when the reaction is complete. So they have to be at the beginning, and they have to be there at the end. Chances are you guys have never heard of them, but back in my day, the big word of environmental destruction was chlorofluorocarbons. You may have seen the acronym CFCs. So if you look on the side of a lot of aerosol products or refrigerators, things like that, it will say no CFCs. CFCs, chlorofluorocarbons, what they do is they interact with the ozone, which is the protective layer that's around the Earth. The ozone blocks UV radiation or some UV radiation from getting to the Earth, protecting us from kind of the more dangerous parts of the sun. So what chlorofluorocarbons did was they reacted with the ozone to destroy it. Ozone is O3, and so chlorofluorocarbons would react with it and just turn it into harmless oxygen. So no longer could it protect us, and so it created the holes in the ozone you may have heard about. Chlorofluorocarbons themselves are CClF3, so it's carbon, chlorine, and 3 fluorine molecules. And those, when they come into contact with HV, so light energy, so from the sun, they produce CF3 and Cl. And so it's that Cl that then goes on to interact with the ozone. So here's the process by which it occurs. So chlorine interacts with ozone to produce oxygen and the ClO. The ClO then goes on to react with another oxygen to produce O2 and Cl. So if we look at the overall reaction here, we see that we start with chlorine, and then it's on this side as well. So we can cross that out. ClO is produced and then destroyed. So the overall reaction ends up being ozone plus an oxygen molecule will give us 2 O2s. So this reaction would happen on its own naturally, but this right here, this process of adding Cl in, is what causes it to be go faster. So ClO, this guy right here, it is created then destroyed. So in terms of elementary steps, in terms of mechanisms, we would call that an intermediate. It's created then destroyed. Cl, on the other hand, is there, so it exists, it's destroyed, and then it's recreated. So something that's created then destroyed is an intermediate. Something that is there, destroyed, then created again is a catalyst. So we recognize Cl as a catalyst because it is there, used up, and then it's there again. So we start with it, and it's still there, so it can go on to react to something else. So it's something that speeds up a reaction without itself being used up. So what you can see then, it's not that a catalyst doesn't do anything, it's not that it doesn't react. It does react, but then after the reaction's over, it's created again. So it's still there, and it can go on to interact with another O3. So that's different from like this oxygen right here. Oops. This oxygen right here is used, and then it's done with. So it reacts with this oxygen, and so it can't go on to harm anything else. But the Cl, it interacts with this ozone, goes through this whole process, it's created again, so that Cl can then go on to interact with another ozone molecule. And so it can keep doing that forever. Each chlorine atom will actually go on to destroy about 100 ozone molecules, and eventually it'll react with something else, and then it'll leave the stratosphere. So chlorine, Cl, obviously you should recognize it as a diatom. It's more stable as Cl2. So this chlorine molecule itself isn't very stable. It will find something else to react with. They say that even today, if we were to completely stop using CFCs, there's enough chlorine molecules up in our atmosphere to where they could go on for about another 100 years destroying the ozone before all of them will go away. So in terms of reaction mechanisms, you recognize a catalyst because it's something that's at the beginning and then at the end, but not in the overall reaction. So it's used and then created again. Intermediates created, then destroyed. So the way a catalyst speeds up a reaction is just by lowering the activation energy. So if we look at this right here, just the single-step process with no catalyst, it's going to require a high amount of energy in order to trigger this reaction and get it to actually happen. So even though there might be plenty of O3 and oxygen up in the atmosphere, unless it gets that amount of energy, it's not going to break apart the ozone. However, if we had a catalyst like the chlorine from the chlorofluorocarbons, it will interact with that ozone to produce the ClO and the oxygen, and that requires less energy for this reaction to happen than for this reaction to happen. So as a result, with this one right here, it's lowering the activation energy to produce the same products, but since it has a lower activation energy than this other reaction right here, that means it can happen a lot easier and it can happen at a faster rate. And the overall reaction for either one of these ends up being the same. Once you cancel out intermediates and the catalysts, you produce the same thing no matter what reaction it is. So both of them are considered exactly the same, just this one has lower activation energy. You're going to see questions every now and then that ask you kind of, if you think of Lachat Layer, so Lachat Layer says that if you stress a system, it'll shift the equilibrium towards products or towards reactants. They might ask you a question then, so if you add a catalyst to the system in equilibrium, how is it going to affect equilibrium? How is it going to shift it? So a catalyst lowers the activation energy for the entire reaction. So here's no catalyst, here's with a catalyst. So in the case of the forward reaction, it's going to lower the activation energy for the forward reaction, and in case of the reverse reaction, it will also lower the activation energy for the reverse reaction. So what that means is it's going to affect the reaction rate in both directions, towards the products and towards the reactants. So really, Lachat Layer says that it's not going to affect the system at all because you're stressing the system on both sides so they cancel each other out. So KEQ, when you add a catalyst, will not change. So it's not going to shift the reaction. Watch out for that. They'll usually try and slip that in when they're talking about Lachat Layer. So, if you add some of this, increase the concentration of this, how is it going to affect the equilibrium? Well, it's going to shift away from it. If you add a catalyst, how is it going to affect the equilibrium? Well, it won't, as long as the temperature isn't changed during the process of adding the catalyst. There's two different types of catalysts that are used in practice. There's homogeneous catalysts and heterogeneous catalysts. Homogeneous, that means the same, and so what we're talking about with homogeneous catalysts is it's in the same phase as the reactants. So, for example, the destruction of the ozone, the chlorine, the ozone, and the O are all gases, so they're in the same phase, so it's a homogeneous catalyst. You can also have heterogeneous catalysts, in which case the catalyst is in a different phase than the reactant, so it looks different. You can actually see the catalyst inside. In the ozone, you won't be able to see the Cl any different than the ozone molecules. With a heterogeneous catalyst, you can see a difference. There are several different practical applications of a heterogeneous catalyst. One is the synthesis of ammonia, which is really important because we use ammonia for a lot of things. One of the biggest uses of it is fertilizers. Fertilizers use lots of ammonia. Cleaning products use ammonia. And so the industrial process for making ammonia is a really tricky one. What that involves is reacting into, so nitrogen, and you can just use atmospheric nitrogen, it's the largest thing in the atmosphere, with 3 hydrogen, which is easy enough to synthesize, to produce 2 ammonia molecules. So it's a pretty simple reaction, really easy to find the ingredients, and we can make this ammonia, which we desperately need. The problem is it's not an easy reaction. It's got a high activation energy, it's hard to trigger, hard to make it actually happen. And so one of the ways that they found to do this is using a catalyst. So the heterogeneous catalyst that they use to create this is a solid transition metal, so it's actually like a chunk, a block of solid state matter. One of the common ones is palladium and carbon. So palladium would be the transition metal. Carbon is just kind of a holster for it, so the palladium's mixed in with the carbon. And you've got this solid, and you just run the gaseous H2 and N2 over this solid block of palladium over carbon. When you do this, you do it at really high temperature, so those molecules actually slam into the surface of that catalyst. And that'll break the bonds and cause them, instead of bonding to each other, like the two H's from bonding to each other, they'll lose that bond right there, and each H will bond to the PD over C. And so what we would get here then is all of the hydrogens breaking their bonds and attaching to this guy, and the nitrogen breaking their bonds and attaching to our catalyst. And so we produce just these single molecules that are all attached to that guy. So this has to happen at a very high temperature in order to break those bonds and get this to go on. So remember that transition metals have what's called a sea of electrons, which means all of the electrons are delocalized. A single electron doesn't belong to a single atom of palladium. Instead, they're kind of flowing around and they share them. That's why metals conduct electricity. And so since those electrons are flowing, that means that these bonds can flow as well. And so they'll kind of move around on the surface of this palladium or carbon, and they can eventually find each other. So as they're kind of skittering around on the surface of that palladium, they will eventually bond 3 hydrogens to 1 nitrogen, so they'll find each other, and this is a pretty stable bond once it's formed. It's just a matter of breaking apart those hydrogens, breaking apart the nitrogens, so that these guys can get together. Once they do get together, though, they're happy and they can skitter off as ammonia. So the ammonia will enter the gaseous phase, and it can then be collected and put into industrial use. And in the end, since this transition metal, okay, this block right here, since it's a catalyst, it's not used up, and so they can just keep using the same one. So then they can just take nitrogen and hydrogen, keep on flowing it over the top of this catalyst, and keep producing ammonia without having to really replace this. Obviously, over time, there'll be some destruction just from oxidation or other things like that, but the catalyst is not used up in this reaction. It speeds up this reaction by lowering that activation energy of this right here so that we can produce more product at a faster rate.